Hello everyone. I am Suvrat and today we'll be discussing Codeforces Div 1 plus 2. Am I audible to you guys? Hello, am I audible guys? Okay, so let's start the discussion. So, problem A, round trip. Petya and Vasya love participating in Codeforces rounds. Vasya made a bet with Petya that he will take part in more rated rounds than him. Initially, Vasya's rating is R0. There will be N rounds conducted in total, each of one of two types. Div 1 rated for all participants, Div 2 rated for participants with rating strictly less than X, and unrated for all others. In an unrated round, Vasya cannot change his rating. If Vasya's rating before a rated round was R, then for any non-negative integer X between R minus D and R plus D, Vasya can adopt a strategy such that his rating becomes exactly X afterwards. Here D is a positive integer. Note that rating may never become negative. Help Vasya determine the maximum number of rated rounds he can participate in. And the constraints are there are 1000 test cases and n is still 1000, and we are given sum of n across all test cases does not exceed 3 4. So expected time complexity would be O of n or O of n log n. So basically this problem says that there are two types of rounds. First of all, div 1 rated for all, and div 2 rated for uh, rating less than X, strictly less than, right? Strictly less than X. And basically in any rated round, whenever we participate, if our initial rating is R, then our final rating can be anywhere between R minus D to R plus D, where D is given. So we need to find out the maximum number of rounds that we can participate in. So let's see the test cases. So first test case, initial rating is 2100, then D is 2100, sorry, X is 2100, and D is 5, and the rounds are div 2, div 2, div 2. So basically to participate in div 2, our rating should be less than X. And since our rating is 2100, which is equal to X, we will not be able to participate in any of the div 2s. So the answer would be 0 for this test case. The next test case is our rating initially is 2098 and X is 2100. Then D is 5 and the contests are div 1, div 1, div 1, div 2, div 1, 1. So basically we can participate in the first contest. Since it is div 1, it would be rated for all. So after the first contest, our rating we can choose any rating from 2098 minus 5 to 2098 plus 5. So from 2093 to 2103. So basically, since we need to participate in as many rounds as we want, and we will be able to participate in all the div 1s, and to participate in div 2 we need a rating of less than x. So what we can do is we can try to decrease our rating. Well, in this test case our rating is already less than x, but decreasing it wouldn't be of any harm. So let's go to 2093, and then we can go to 2088, and then we can go to 2083, and then again, and so on. So basically we can participate in every contest. So this is 6. Then the next test case, 2115 is our initial rating. Then X is 2100. Then D is 226, and 221121. So we will not be able to participate in these two contests since our R naught is greater than X. But then we can participate in these 3 div 1s, and our rating can go from 2115 minus 226 minus 226 minus 226. So basically this will be somewhere around 600, somewhere around 1400, I think. So which will obviously be very much less than x. So we can participate in these two as well. So the answer will be 5. So basically the thing is, we will always try to decrease our rating as much as possible. Because if we decrease our rating as much as possible, we will be able to participate in as many contests as we maximally can. So basically this, and since it is mentioned in the question that the rating may never become negative, so basically at one point our rating will become 0, and then it will stay at 0, and we can participate in every further contest. So we will try to decrease our rating as much as possible, and we can just count on how many contests we can participate. So the solution will be of O of n. We can just iterate over the string s, and we can check if I is div 1. We can simply make our rating maximum of 0 and r minus d, so that we don't go negative. And if the contest is div 2, basically if our rating is greater than x, less than x, we can again do the same operation. Else we need to continue, and we just need to count the number of contests that we are participating in, and that would be the answer. So I'll show you guys the code for this. So I take input r naught x d and n, and then basically I iterate over the string s. So if it is a div 1, we can always participate. So count is the number of contests that we have participated in, and r naught would become maximum of r naught minus d and 0. Else if it is a div 2, if our rating is greater than equal to x, we will have to continue. Else we can again do the same and count plus plus. And in the end, we can just output count. So that was the solution for problem A. If you guys have any doubts, you can ask. If r is already less than x, then why do we need to subtract? Yes, you do not need to subtract further, because basically if we can participate in one div 2 in every other contest, if every further contest you will be able to participate. It's just choice, your choice. If you want to subtract or if you don't want to subtract, you will get the correct answer regardless. Okay, so we try to decrease every time but increase only if r minus d is less than 0, only if r less than x, or si is equal to 1. Why this approach don't work? Please tell, sir. Um, we try to decrease every time but increase only if r minus d is less than 0. If you actually, why would your r minus d, you don't need to increase basically if your current rating is 0. Basically in the question it's mentioned that you can choose any non-negative integer x between r minus d and r plus d. So non-negative integer x includes 0. So if r minus d and r plus d includes 0, then you can go to that rating and you can stay there. You in further contests just don't change your rating anymore and you'll be able to participate in all of them. Did you understand? Not increasing but staying at same also give error in pretest 3. I don't see why that would give an error. You can just paste your code in the comment and I'll try to see it. I cannot debug live here, but that approach should work. It is correct. You can just stay at 0 and just participate in every next contest. So let's move on to the next problem, I think now. So the next problem is make connected. So next problem is make connected. You are given an n cross n grid where some cells are colored black and the rest are white. You may paint some of the white cells black to achieve the following conditions. First is there is at least one black cell. Second, all black cells must be orthogonally connected. That is, it should be possible to go from any black cell to any other by crossing several vertical or horizontal cell borders while visiting only black cells. You can't go directly through the corner of a cell. So, and there are no three consecutive black cells aligned vertically or horizontally. You can't paint black cells white. Determine whether it is possible to paint some white cells black in order to satisfy all the conditions. And the constraints are t is less than equal to 1000, n is less than equal to 100, and it is guaranteed that the sum of n over all test cases does not exceed 2000. So basically, expected time complexity would be n square or n square log n. So basically in this problem, we are given a grid with some elements black and some white. And what you can do is basically color the white cells black. And you can perform this operation as many times as you want. And we need to tell if we can transform the grid into a grid that follows these three conditions. So basically, the first condition given is there is at least one black cell greater than one black cell, greater than equal to actually. And the next condition is all black cells must be orthogonally connected. All black cells must be connected And the last is no three consecutive black cells align vertically or horizontally. No three, no three black cells align. So basically, let me just explain the second and third condition. So the second condition is that all black cells must be connected. So that means that all the black cells must be like this. They must share at least one edge. For example, if these cells are black, they form a connected, they are all connected, because from any black cell I can travel horizontally and vertically to go to any other black cell. But if they are like this, then these black cells are not connected, since I cannot go from this black cell to this black cell moving through only black cells. So this is not, and this is connected, and no three black cells are aligned. So these type of black cells should not be present. So let's see the test cases. The first test case, you can just paint this cell as black, and that would be following all the three conditions. So yes. Again, the second, it is a yes, second test case. The third test case, the test case already follows the condition of all the black cells being connected and no three black cells being consecutive. So third, third test case is also yes. And then the next test case, let's see that. So this is black, this is black, this is black. So we need to paint the white cells black now in order to connect them. So what we can do is we can paint this cell and this cell, so that now all these form a connected component, and there are no three consecutive black cells. So the answer for this test case would be yes. Let me mark the colored black cells with some different color. So black, black. Then the next test case, in the test case only, there are three black colors which are aligned horizontally, and we cannot paint the black cells white. So the answer for this test case would be no. Then the next test case, let's solve that. It's 3 by 3. Okay. So this is black, black, black. So let's try to connect these two first. So how can I connect these two? Using this black cell, I cannot color this black cell, because then three black cells would be aligned horizontally. So my only option is to color this black cell and then color this black cell to connect these two. And now to connect this black cell as well, I need to put a black cell here, and I cannot put a black cell there because then these three will be horizontally connected. So basically the answer for this would be no, since there is no way that I can connect these two black cells or these two. So answer will be no for this test case. Now in the next test case, again there is already three black cells in a straight line. The next test case, so black, black, black and black. So what we can do is we can paint these two cells black and they will be connected. So answer for this is yes. Then the next, we can paint these two cells black and they will form a connected component. So answer for this is also yes. Then this, let's see that one as well. So, okay, black, 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 black. So in this, there is no way to connect these black cells, because any cell that I try to color black would make a horizontal or vertical consecutive 3 blacks. So basically there is no cell that I can color black. So the answer for this test case would be no as well. Then the last test case, let me just draw it here only. Black, 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 and then black, black. So to connect these, we can do this. We can do this to connect these two. So answer for this test case is yes. Or what we could have done instead of this. Okay. There is only one way to color these. You can only follow this path. So basically the answer for this test case is also yes. So let's try to analyze the question a little bit. We can see that we are coloring only in these types of patterns. We have already seen that through the test cases. We see this pattern in all the test cases. So let's try to analyze what is this about. Okay, so let's say I have a black cell here. So using this cell, what other cells can I connect to? Basically, if this cell is black, the next cell that I can connect to is this, either this or this. So let's just do this. If I color this cell as black, then I have only one option. I have to color this cell. Now again I could have colored this cell, but let's move on to this side. So if we follow this, we can color like this. And if we had followed this path, we would have colored like this. So basically, is there any other way to color these two cells? Let's say I have a grid and I need to color these two cells black, and we are given these two cells black and we need to connect them. So what are the ways that we can do this? Can we do it through here? No, we cannot do it through here. So we have only one choice, to follow this path. Basically, we can only follow this path and connect these two cells. So even if we had gotten this cell, then also if our question had this cell, then again we would have to follow this path only. We would again have to do this. There is no other way. So if we get this cell or this cell or this cell, we would always have to follow this path. We would always have to follow this path. So This green is for these cells. And symmetrically, what we can say is if we had these cells colored, we would have to follow this path. You see that? And for this cell, for the cells in between, we could have taken any path. It wouldn't matter. We could have taken any path and ended up at that cell. But if the cells are on this diagonal, then we would have to take the green path. And if the cells are on this diagonal, then we would have to take the blue path. Now, apart from these cells, is there any other cell that we can color using this black cell? What if we had the black here? What if the other black cell is given in this cell? So, is there any way we could have colored that? We could have connected without forming this horizontal line. So, using this black cell, there is no way to connect that cell because we can only connect two horizontals. We cannot have three consecutive blacks. So, basically, we won't be able to connect that. So, the only cells that we can connect using this black cell would be these. So, if we have a black cell in any other cell apart from these, then the answer would be no. So, this is our observation. Let's try to take some general point B rather than this corner point and see what happens from there. So, if we had the point here, now where could we have gotten? We could have gotten here. We could have gone there. Or what we could have done, so these cells we can go. We can go to all of these cells, right? Or we can now also move like this. So we can also go to these cells. So basically, this extends our understanding of what all cells we can color using one cell. We can connect through this cell. So basically, we can connect in diagonals. So if we have a point, if we have a color black here, we can move in this diagonal, we can color this diagonal or this diagonal or this diagonal, or we can color this diagonal or this or this. So basically, if any other black cell is in other than these diagonals, then the answer would be no. If any black cell is in cells other than these, then the answer will be no. So this is our first observation. So we have narrowed down the problem a little bit. Now, does it matter if we have any number of black cells on these cells, or even in these cells we have some restrictions? So let's see that as well. So let's say that I have this black cell here, and we can go here, right? We can connect all these cells. Also this, and also this. So we can connect all these cells. This diagonal, this diagonal, this diagonal, and this diagonal, this diagonal, and this diagonal. So we can connect these cells just like how we saw these three diagonals and then these three diagonals. So we can connect these cells. So let's mark two of these cells as black and let's see if we can connect them. So first of all, what if they are on the same diagonal? So let's choose this diagonal and let's mark these two cells as black. So can we connect them? So what we can do is we can go like this and then we can go like this. So if the blacks are on the same diagonal, we can connect them. So basically, if one black is here and the other two are on this diagonal, we can connect basically them with this black. So let's analyze other cases as well. So what if again I had one here, I had one here, and I had one here. What if I have another B here? So now these two diagonals I have, and on both of the diagonals I still have two blacks. So can I still connect them? So let's try to connect them. So this, and this. So basically again I can connect them. So the property still holds true. If the blacks are on the same diagonal, then we can connect them on the same. Actually, let me rewrite this a little bit more clearly. If the blacks are on two adjacent diagonals, and I am talking about diagonals like this, then we can connect. So another property, observation 2. So now we have seen that we can connect diagonals like this. Can we connect diagonals like these? Because these diagonals are also, we also saw that these diagonals could also be connected. So let's see that two of the diagonals can be connected or not still. So let's put one black here, one black here, and one black here, and one black here. So again, can we connect these? So yes, we can, and we can just follow this route. And you can see that all of the positions get connected if we follow this specific pattern. So anywhere, if on these two diagonals, anywhere two blacks were there, on any cell, if black was there, we can connect them. So basically, if blacks are on two adjacent diagonals, doesn't matter this or this, any type of diagonal will work. So then we can connect them. So this property seems to be true. Now let's see if the blacks are not on the same diagonal but on different diagonals. So let's take this diagonal B. So this diagonal will be adjacent. So let's take this black, and this is another adjacent diagonal. So let's take this cell as black also. So now can we connect them? So to connect this black cell, I have only one route. I can connect it like this. But to connect this black cell, I have the same route. I would need to follow this route, but I can't follow both routes because then these three and these three would be making three consecutive pairs. So I can only follow either this or this. So basically I won't be able to connect both of these blacks. So in a case like this, I cannot connect. Let's try. If one black is here, one is here and one is further back. So let's see if we can connect them now. So again, this black can be only connected like this, and to connect this black, we can only follow this path. So basically again, these three will be forming a consecutive pair. So again, no. So basically we are seeing that if two blacks are on two different diagonals which are adjacent, there is only one path we can take to connect them. So basically if we don't take this path, then we don't have any other choice. And if we take this path, now we are not allowed to go into this diagonal, because the moment we go into this diagonal, we will be forming a consecutive pair. So I'll repeat my point. So let's say that I need to connect these two blacks, right? So I'll have to go from here to this diagonal, and I can only follow this part to connect these two blacks. Now to connect this black, I need to again go to this diagonal, and this is the only path that I can use to connect these two blacks. So basically, if one of my black is on this diagonal, I will have to move here, and if one of my black is on this diagonal, I will have to move here, and if there are blacks on both the diagonals, then basically I will be forming a pair of forming a consecutive pair, which is not allowed. So basically this is another observation. The blacks can only be on two adjacent diagonals, because I cannot be moving to both the diagonals. So the blacks can only be on two adjacent diagonals. Now, is there an exception to this case? So basically, let's say that I have gone to this diagonal, and I have also gone to this diagonal. So basically I will color these two cells black. So now this is an exception, because in this case if these two, if we are, let's say, given these three cells as black, so we can see that they are on three different diagonals, yet they are still connected. But the problem here is, now if I place any more block on these diagonals, we cannot connect any other block on these diagonals. Basically I cannot connect this block, I cannot connect this block, or I cannot connect this block, or I cannot connect this block. What I can do is I can switch my perspective and make these two diagonals, but if I consider it like this, I'll not be able to connect further any more cells. So basically this is an exception, and if you, what I can do best in this case is make this cell black. So our blacks will look like this, and once I have this, once I have four blacks arranged like these, now I cannot connect these four blacks with any other black, because let's say if I have a black here, I will not be able to color any of these cells black, because that would make a consecutive pair, which is not allowed. So if our test case is having a block like this, there cannot be any more blacks which are not directly connected. So Basically, if you guys paid attention, we also had a test case like this, which hinted me towards this. So either in the question, we can have a test case where the blacks are like this, then the answer will be yes. Either, if not, they must be on two adjacent diagonals, because we saw that if they are on three diagonals, then we won't be able to connect them. So we can only connect blacks which are on two diagonals. We can only connect two diagonals at a time. We can choose, it's our choice, if we want to connect these two or we want to connect these two, we can choose, but we will have to choose just two diagonals. So the final solution would look something like this. Case 1, all the blacks lie on two adjacent diagonals like this. So basically they lie on diagonals like this. Case 2 would be they lie on diagonals like this. And the last case will be basically we have a box type of thing in our grid and these are the only black colored cells. So in these three cases, the answer would be yes, else the answer would be no. So we can also you can also see it like this. If basically we are connecting these two diagonals, then now we cannot color this cell black, we cannot color this cell, we cannot color this cell, we cannot color this cell. So basically we are kind of cut off. If we connect two diagonals, then we won't be able to connect to anywhere else on the grid. So all the blacks must be on these two must be on diagonals like this or this. So now our next task is, how do we implement this? How do we implement this in O of n square? So let's start by checking with diagonals like this. Okay, so let me make a grid. So this is a very common trick which is quite often used in CP. So let me mark the indexes. So now how we will identify if the cells are on, let's say, these two diagonals. So there is a very interesting property. You can see that when we go from this cell to this cell, we subtract 1 and we add 1. Basically, here we are going from 4 to 3, here we are going from 1 to 2. So the difference remains same. On all the points, on all these points, the difference, let's say that these cells are x and these cells are, this coordinate is y and this coordinate is x. So basically on this line, x minus y is equal to a constant. Basically 1 minus 4 minus 3, 2 minus, just a second, sorry, we subtract 1 and we add 1, right? So the sum would remain constant. If we had added 1 to both the coordinates, then the difference would have remained constant, but here we are subtracting 1 and then adding 1, so the sum remains constant. So on this line, x plus y is constant, which is 5. Here 1 plus 4 is 5, 2 plus 3 is 5, 3 plus 2 is 5, 4 plus 1 is 5. And we can take another diagonal as well. So this, here also we can see that 1 plus 3, 4. And 2 plus 2, 4, 3 plus 1, 4. So basically what we can do is, we can check if we can check for all the black cells and see if they lie on just these two diagonals or not. So basically we can check for all the black cells on what diagonals do they lie, and if they lie on just two diagonals which are adjacent, then that would be your answer. And For the other case, what we can do is, for this case, again for this line, let me draw the line again. For this and for this line, so for this line x minus y is 0, and for this line you can see x minus y is minus 1, 1 minus 2 minus 1, 2 minus 3 minus 1, 3 minus 4 minus 1, and this is 0. So basically x minus y is constant over these lines. So what we can do is, we can maintain multisets which will hold the I minus I plus j, and a multiset for I minus j which will hold these values. So after we create this multiset for all the black cells, we can check if the multiset has only two values which are adjacent to each other, and if then the answer would be yes. Or we also need to check for the third case, which is this, which basically means if the element, if all the black cells have only are only like this, then the answer would be true, and that can be handled very easily. We can just maintain two more multisets for the ith index and jth index. If there are only two different I indexes and which are consecutive, and two different j indexes which are consecutive, then again this condition would be true, and the answer would be yes. So your further doubts, I'll just clear them. I'll show you guys the code once, and hopefully that clears the implementation doubts. So basically, I take the input as a grid of n into n. Then I maintain four multisets of some difference x coordinate and y coordinate. So in this multiset, I just insert the sum of the coordinates of a black cell, difference of a coordinates of a black cell, and the x and y coordinates of a black cell. So basically, if x dot size is less than 2, that means there is just one or less than one black cell. So x dot size would be just a count of the black cells. So if the count of black cells is 0 or 1, then the answer would straightforward be yes. Else we need to check. So the three cases that we need to check for. So this is actually the third case, and these are the first and second cases. So basically, first case would be, simply we can see that the highest sum minus the lowest sum should be less than equal to 1. That must mean that they are either on the same diagonal or on adjacent diagonals. And similarly, in difference also, we can just see the highest value minus lowest value. If that is less than equal to 1, then that means all the black cells are on the same diagonal or adjacent diagonals. And then checking for a box. So for box, what we can do is, we can see the range of x-axis and we can see the range of y-axis. If both the ranges are less than equal to 1, then that must mean that the elements are inside a box. So these three conditions we need to check, and if any one of these is true, then check will become true, and if check is true, then answer is yes, else no. So that was the solution for problem B. If you guys have any doubts, you can ask. Just a small question. This time you are not providing solutions for problem D. Basically, problem D was quite hard. You guys can see that only around, actually during the contest, this was around 700, and 700 in div 1 plus 2 is like, you are almost a master. So basically, even I couldn't solve D. I had an approach, but I couldn't make it work in the given time. So we'll not be discussing that. C was quite easier than B in today's contest. So, yeah. And D was quite difficult. So I'll wait for a minute and then move on to the next question. Okay, so let's move on to the next problem. So you are a customer in a store and want to buy n items. Each item I has a price AI such that 1 is less than equal to AI and AI is less than equal to X, where X is a loyalty factor. Your loyalty level in the store is defined as S by X, floor of S by X, where S is the total cost of items purchased so far. Initially, S is equal to 0. So if you buy an item with price P and your loyalty level increases as a result of this purchase, you earn P points. Your task is to find the maximum number of bonus points you can earn by choosing an optimal order of purchase for the items. And the constraints for the problem is T is still 2e4 and N is still 1e5, X is still 1e9, and AI is given from 1 to X, and the sum of N over all test cases does not exceed 1e5. So basically the expected time complexity would be O of N or O of N log N. N square would again not work here. So basically we are given a shop where the ith item has price AI and AI is given from 1 till X, and we have a score, loyalty level. So basically loyalty level is S by X whenever we purchase an item, let's say with price P, and our loyalty score increases, then we earn P points. We need to find what maximum points we can earn. So let's before looking at the test cases, let me make a few observations right away. So basically our loyalty score is first of all S by X, floor of S by X. This is our loyalty score. And we are awarded points when we make a purchase. We are awarded P points when we make a purchase of cost P, and our loyalty score increases as a result of that. So basically, when will the loyalty score increase? So let's actually plot X with S, the loyalty score. How will this look like? So this will basically from 0 till X, the score will remain 0, and at X, the score will become 1. Then till 2X, the score will remain 1, and then it will become 2. So basically, the graph will somewhat look like this. So whenever our score becomes greater than X, we will be awarded points. When it becomes greater than 2X, we will be awarded points. When it becomes greater than 3X, we will be awarded points. And we need to maximize the number of points, right? Maximize the number of points. So we need to maximize number of points. So what we can do to maximize the number of points? Two things, right? Try to increase the number of purchases where we earn points. So this is obvious that if we make more purchases where we are earning points, we will be earning more total number of points. That is one factor. Another factor would be earning more on each time we increase loyalty score. So basically, every time we increase loyalty score, we need to try to increase by using some cost, by buying some expensive item. Basically, we'll try to buy expensive item every time we increase our loyalty score. We are about to increase our loyalty score. So these two factors, there are these two factors that decide how much we earn. So let's focus on the first factor first, the number of purchases where we earn points. So number of purchases where we earn points. So let's look at this. So we saw the graph somewhat look like this. So whenever our score crosses these boundaries, whenever our score crosses these points, we will be awarded a chance, we will earn that amount, right? Whatever amount we use to cross this, we will earn that, P1, P2, P3, right, so on. So basically, what are the maximum number of times that we can cross this? That would be basically total sum upon X floor. So I'll help you guys understand this through a test case. Let's take number of loyalty factors 10. So I think let's take this test case only. 1 2 1 2 1 2 1 2 1 2. So 1 2 1 2 1 2 1 2 1 2, and the loyalty factor we are given 2. So what is the total sum? 1 3 4 5 6 7 8 9 10 11 12 13 14 15. So 15 is the total sum, and upon X would be 7, right? So what does this mean? So loyalty score can go a maximum till 7, and minimum it would be 0. So we can increase it a maximum of 7 times only, right? It will be increased a maximum of 7 times only. So maximum number of turns we will earn money on is equal to 7. Actually not 7, that would be specific for this case. total upon X floor. So this is our first observation that we are making. Now the other factor that we had, basically earning more on each time we increase loyalty score. So now since we know that the maximum turns that we can earn on are total by X, so maximum possible score would be always less than equal to sum of the most expensive items. So basically, if we add the total sum upon X most expensive items, that would be the upper limit of maximum possible score. Now, let's think about, is it possible to always attain this score? Can we always attain this score? So basically, here comes this part. So we are given AI is all between 1 till X. So let's say that uh, our score currently is here. Let's say our score is here. So there are two possible options. We can either buy a small cheap item and we can just move from here to here, or we could have bought an expensive item and gone from here to here. Now the limitations of AI is from 1 till X, and we know that once we buy all the items we will always end up at this point, the total point, total. We would always have to end up here. We would always have to end up here, no matter how we make these jumps, no matter at what point what do we buy, it does not matter. In the end we would always reach this point. In the end our loyalty score will always be total upon X floor, right? And we are given that AI is from 1 till X. So how long can this jump be? It can never go from here to here, because AI is from 1 till X, right? Even if I am at the boundary and my AI is equal to X, I would still only be able to go to the next boundary. So basically, no matter what I do, I won't be able to skip a level. I won't be able to go directly from here to here, no matter what I do. So basically, this is another observation. No matter in what order the purchases I make, the total number of purchases where I earn points will be fixed and equal to total upon X, floor of total upon X. So this is another observation. That no matter in what order I make the purchases, I would always end up at this score. I would always earn these many times. So now, basically, this is fixed. This is fixed. We don't have this condition anymore. So earning more on each time we increase loyalty score is our only concern now. And now this problem is very easy. What we can do, we can follow a very simple greedy strategy. We can keep buying cheap items until we are at a score where we can jump to the next score by buying a expensive item. And this strategy will uh, give us the maximum possible score equal to this, since we will be only making the purchases with the most expensive item available in the shop, purchases where we earn points, since we will only be making with the most expensive item, so we would always have this maximum score. So to implement this, we can do a simple 2-pointer approach. What we can do is, we can first sort the array, sorted, and let's say our score is S. So S must be S must look like QX plus R, right? QX plus R. So this R will be the remainder when we divide S by X. So we need, if we are at a point like this, we need X minus R more. What is S actually? What do we call S? Loyalty level to make S is equal to Q X plus 1 plus 0. So basically, if we can make a purchase of cost more than this, then our S by X will go to the next level. So we need to make a purchase of cost more than X minus R. Right, so let's keep this in mind. And what we can do is maintain 2 pointers, P1, P2, and we will keep on adding from P1 till a point where the value at P2 becomes greater than X minus R. Because as we keep on adding the cheap items, our R will become smaller and smaller and smaller. And there will come one point where our R is, our R will become larger and larger and larger. And there will come a point where it is large enough so that X minus R would be less than this value. So we can buy this and our score will increase, and then we can follow the same strategy. And if we are at a point that if on buying this our score will increase, we can buy, and we will just increase our score by buying these expensive items. So from the last total by X, sum of total by X elements would be our final score. So I'll show you guys the implementation for this. So I take input the vector v and I sort it. I maintain 2 pointers P1 and P2, and answer will store the score for me, and answer v vector will store the items of the prices of the items, and S is my score. So basically need is how much do I need to progress to the next level. So that is X minus remainder of X, remainder. And so if the large pointer is greater than equal to need, then we can simply add that value to our score, and also we can add that value to our answer since we are progressing to the next level, and we can push back that price to our answer vector. And if this is smaller than need, then basically we can just add the cheap item and push back it into the answer. We don't need to increase our total bonus points because we are not progressing to the next level. Since if the largest possible price cannot make us progress to the next level, then there is no way that this cheap item will progress us to the next level. So basically, we don't need to update the bonus points here. So the bonus points will always be updated in this if, and this if will only have the most expensive items, and we subtract P2 by 1 on every time we buy an item and increase P1 by 1 every time we buy an item, and then see out answer and see out this. So that was the solution for problem C. If you guys have any doubts, you can ask. Okay, so I think you guys don't have any more doubts. So I'll end the live stream now. Thank you.